Hello and welcome to our first video for Chapter 3, where we will be discussing experimental error. One of the things I really hope you come away from this class with is an understanding that whenever we make a measurement of any kind, it has error associated with it. The one exception to that I can think of is if you're counting numbers of things, right? If you know that there are 10 items, there are 10. But when we're thinking about analytical chemistry and measuring amounts of things and quantitative analysis, all of the measurements that we make have some amount of uncertainty to them. And that varies a lot depending on the technique and depending on the skill of the person doing the analysis, if it requires manual manipulation of the reagents and things like that. But all measurements have some amount of error that's present. Sometimes the error is very small, sometimes it's very large. That's an important thing to know about any measurement that's made. Now, this chapter is mostly about how do we keep track of that error. And to start with, we're going to discuss significant figures because this is a key concept in writing numbers down, writing values down, and acknowledging that they are not completely precise to an arbitrary number of decimal figures, but any number that we're given has some uncertainty to it generally. All right, so this should be review, but just want to make sure that you remember how to account for significant figures if you haven't thought about it for a while. And we'll see that these significant figure rules really come from a more fundamental examination of error in the idea of propagation of uncertainty, which we'll get to at the end of this chapter. Okay, so first of all, what are significant figures? So the significant figures of a number are the minimum number of digits needed to write a number in scientific notation without losing precision. And we specify that in scientific notation to make it clear that significant figures, we often have zeros that are placeholders, and we'll go over those rules in just a minute. And so if we write things in scientific notation, then we don't have to worry about did we add extra zeros at the end of a very large number or have a bunch of extra zeros at the beginning of a very small number. If we write in scientific notation, that issue is not relevant anymore. And the idea is that we write it without losing precision. Significant figures I feel like are easiest to understand with examples. So we'll look at a couple of some numbers here. If this were an in-person class video rather than a video, I'd just ask you to tell me how many significant figures. I'll write down a few numbers, and I'd like you to tell me how many significant figures are in each of those numbers. You're not going to be able to actually tell me, but I'd like you to pause the video and think about it for just a second. So we have the numbers 142, 142.7, 102.89. So pause the video. How many significant figures does each of these have? Okay, hopefully you paused it and actually thought about this. So 142 has 3 sig figs, and I'll usually use this abbreviation. If we write this in scientific notation, this will be 1.42 times 10 to the 3. And so we need 3 digits to be able to write this out in scientific notation without losing any precision. All right, the next one has 4 sig figs because we have now 4 decimal places that matter. So we have 1.427 times 10 to the 3. So now we have that extra decimal place in the tenths place. And 102.89 has 5 sig figs, because again, if we write this in scientific notation, we have 1.0289, still all times 10 to the 3, but we need 5 digits to be able to write that out. So one question that often comes up with significant figures are zeros. When are zeros significant? Sometimes they are, sometimes they aren't, and it depends on the situation. All right, so basically, zeros are significant when they're not just placeholders. So again, we'll look at some examples. So zeros are often used to just sort of shift a number to, the correct order of magnitude, power of 10. So if we have, say, a number like 0.00506, doing one that has zeros that are both significant and not significant on purpose. All the leading zeros here, these are all just placeholders. Because if we write this in scientific notation, and this is often the easiest way to see this, this will be 5.06 times 10 to the minus 3. So those zeros disappear if we write this in scientific notation, which means they're just placeholders, not significant. But this 0 here in the middle is required to write this number out, right? This 0 does matter. It's not 5.16, it's not 5.26, it's 5.06. So this one is significant. Okay. What about if we have a trailing 0, right? So maybe we have, instead of 5.06 times 10 to the minus 3, maybe we have 50600. This one is actually ambiguous, but probably only has 3 significant figures. It depends on whether those final 2 zeros are exactly 0 or this number has been rounded. Right, so this would be 5.06 to the 10 to the 4th. So this is probably 3, and we would need some way to indicate whether these zeros are significant or not. So one way this can be done is to put a decimal place at the end. That would indicate that they are significant, and this would have 5 sig figs instead. Or if you have one additional significant figure, I mean, the simplest way is just always write it in scientific notation. That makes it very clear. And when you have a decimal, maybe it's 0.00560, this trailing 0 is significant. It's always significant because it's indicating that we know this number precisely to that extra decimal place.